Good everyone, my name is Graphics. In today's problem on open channel flow, we'll be looking at a trapezoidal channel, right? And the question goes like this. It says, a channel of trapezoidal section has bed width of 8 meter and bed slope of 1 in 4,000. If the depth of flow is 2.4 meter and the side slope of the channel are 1 horizontal to 3 vertical, determine the average flow velocity and the discharge carried by the channel. Also compute the channel shear stress at the channel boundary, right? So the first thing we have to do is to write out our parameters, right? So from the parameters, we're told that the bed width is given to be 8 meters, right? And the bed slope is 1 in 4,000. We use S naught for the bed slope and B for the bed width. And we're given the depth, right, of 2.4 meters. Is that taken? So the depth of the channel is given to be what? 2.4 meters. I'll use Y to represent it, or you can use your D to represent it if you want to. Then we use Q for our discharge, which is what we are looking for. We use V for the velocity, which is what we're looking for. We use shear stress, which is what we're also looking for, right? And the side slope is given to be 1 horizontal to 3 vertical, which is a constant given to be what? 55. Now, diagrammatically, this is what it is trying to tell us. If I have my trapezoidal section this way, remember, it is the combination of a rectangular channel and a triangular channel. The bed width here is 8 meters. The bed slope is 1 horizontal and 3 vertical. You place it here. The depth of the flow is given to be what? 2.4 meters. Right? Now, what we should do here is this. If I should section this, like if you look at this channel, I told you the combination of what? A triangle and a rectangle. So if you now look at it closely, right, if I should move from this point upward here and here upward here, discover that will bring out a what? A rectangle. This is section 1, section 2, and section 3. You can see that? So if I should do that, I should start naming them. Let's say here should be E, F, L, N, M, and what? And G. Is that taken at this point here? So what I'm going to do is that you discover that FL, right, is nothing as saying GM, which is 8 meter, 8 meter altogether. Now, for me to be able to get MN, right, the distance between M and what I will do is I am going to use the ratio of the side slope times the height, right? Because using the ratio of the side slope, which is 1 in what? That is 1 horizontal to 3 vertical. So it will be 1 over 3 times what? Times the depth of this channel here, which is given as 2.4. So we multiply 1 over 3 times 2.4, we have 0.8 meters. Similarly here also the same thing, 1 over 3 times 2.4 in between G and E, we have what? 0.8 also here. That's what we have there. Is that okay? Now we'll move forward. So from here, we can easily calculate, first of all, the area of this channel, just to save our time. So the area of this channel is given to be what? Half A plus B times H, right? Now, if you look closely, the A here is representing the bed width here, just the bed width, and that is 8 altogether. And the B here is representing everything up here, right? That would be 0.8 plus 8 plus 0.8 altogether, and that is what? 9.6. While the height here, the H here, representing the depth Y, and that's going to be what? 2.4. So by the time you do the needful, you add 8 plus 9.6 multiplied by 2.4, then divided by 2. That will give us what? 21.12 meters square. So we successfully calculated for the area to be what? 21.12 meters square. So I'll just write it out here, A to be this. Altogether. Similarly, after calculating for the area, we have to calculate for what? The perimeter. Now calculating for the perimeter, look at this closely. If I should consider, right, triangle MNL, I bring it out. This is what it is giving me, which we know that the ML, which is the depth, is given to be 2.4, MN is 0.8, and we're looking for what? For LN. Is that okay now? So we apply the Pythagoras theorem that says that my NL or LN square, the hypotenuse square, is equals to the square of the opposite plus the square of the adjacent. So we have LN square is equals to 2.4 square plus 0.8 square. So by finding the needful, my LN will now give me the square root of the square of 2.4 plus the square of 0.8. That will give us 5.76. That will give us what? 6.4 altogether. So the Z here, the ln, will now give us 2.53 altogether. So 2.53 is what you have here. So the perimeter now, you add all the sides that has what? That the water or the liquid has touched. Is that okay now? So it's going to touch the EF plus it will touch the FL plus it will touch the LN altogether, and we know that LN is equals to EF. How good? So we now write that the perimeter here will now give me 2.53, right, for the LN plus 8 for the FL plus 2.53 for the what? For the EF altogether. So the nutshell, perimeter will now give us 13.06 meters. So that's our perimeter. So that is the first thing you do, calculate for to make things easier for you when you're given anything involving open channel flow. First of all, calculate for the perimeter, weighted perimeter, and what? The area. All good now. So from here now, we will now start the needful here. So calculating for the discharge, Q will now be giving us area, weighted area times what? Velocity. We know the weighted area already. So what we'll calculate for now will be what? For the velocity. So we know that the velocity is giving us what? The Chiesi constant times the product, the square root of the product of the radius hydraulic radius times the bed slope. I'll call that my equation 2, right? So for the hydraulic radius R is given as what? Weighted area over weighted perimeter. We know my weighted area that I calculated for is given to be 21.12, and weighted perimeter calculated for is given to be what? 13.06 altogether. So when I input this value into the formula here, we'll be having our answer here. We'll be giving us the hydraulic radius here will now be giving us 1.617. That will be our hydraulic radius, 1.617 meters. How good? Now we've gotten hydraulic radius. The next thing that we should be calculating for, we already have them, so we put it into the equation 2 above. So the velocity now will now give us the Chezy constant times the square root of the product of r s naught. So what is the Chezy constant here? Chezy constant here is giving us 55 times the square root of the hydraulic radius is giving us 1.617 times the bed slope, which is 1 over 4,000, and that will give us 0.00025. So the velocity here will now give us, if you look for the square root of 1.617 times 0.00025, right? Then multiply it by 55, you'll be having 1.1058. That will be the velocity, meter per seconds. So we've gotten a velocity, that's the average velocity. Now we'll now input our value A and V into equation 1. And we know equation 1 is telling us that the discharge is equals to the area times velocity. So what is my area? 21.12 times the velocity 1.1058. So my discharge will now give me 23.36 meter cube per seconds. That is our discharge here. Now the next thing we should do here, we're told to look for, we've gotten the discharge, we've gotten the velocity. Now the next thing is what? The shear stress at the boundary. So we use this to represent my shear stress, right? And for shear stress, we say that is equals to what? The specific weight times the hydraulic radius times what? Times the bed slope. Are we good? So this will now give us the specific weight is given as the gravity times what? Times 9.81 times density of water. So 9.81 times 1000 will give us 9810, multiplied by the hydraulic radius, which is given as 1.617, multiplied by the bed slope, which is 1 over 4000, all together. So by the time you do the needful, you multiply 9,810 times 1.617 times 0.00025. We are going to be having 3.97 Newton per meter square. That will be the shear stress at the boundary. So we have successfully calculated for the discharge, velocity, and the shear stress at the boundary in a trapezoidal section. And we've also, if you want to watch and learn on how to calculate the discharge in a rectangular section, you can click on this link at the top right corner here. You can see that. And also, if you want to learn how to calculate for the discharge in a triangular section, you can click on the link at the top right corner here also. So if you have found the video helpful, please don't forget to like, subscribe, and also share the video. Thanks for watching.